Hi guys, welcome to a new video. In this opportunity, we want to solve this problem on which a cube pushes a billiard ball. The problem says, a billiard ball of mass m and radius r is hit by a cube and its center of gravity gets velocity v0. The momentum passes through the center of gravity and the friction coefficient between the table and ball is mu. How far does the ball move before the initial gliding motion changes to a pure rolling motion? Okay guys, let's see what's going on here. Initially, we can see that the cube hits the ball just at the center of it. So the ball is hit just at its center, and the momentum passes through the center of mass. We know this is a solid ball and the center of mass is just in the geometrical center of the ball. The coefficient, the friction force goes in the opposite direction of the motion, right? And the velocity that the ball gets when it's hit by the cube is v0. Alright? So, what we can do here is to write the torque that the ball gets due to the friction force. For example, we will write the formula ds is equal to f multiplying r. What is f? Okay, f, as we know, is the friction force that is opposite to the direction of motion. Alright? And r is the radio of the ball. Okay, so by definition, the friction force is defined by mu, where mu is the coefficient friction, the weight. The weight in this case of the ball is mass multiplying the gravity. And all these terms are multiplying the radio. Okay? So we have here that F is the friction force, mu is the friction coefficient, and obviously m and r are the mass and radio respectively. So let's call this equation number 1, and we will write it down like this, and let's call this equation number 1. Okay, this is the torque about the center of gravity. So this force is causing the torque about this center of gravity. Okay guys, so I will erase this. I don't want to have too many lines on the illustration. I want to make it that is easy to see. But we know that this force is causing a torque around the center of mass. Okay, we know the center of mass is just at the center of the ball. Okay, But by definition, we also have the torque. The torque, ds, we will call this torque tau, by definition is theta omega dot. So what is theta? Theta is the moment of inertia, or the inertia of the body in this case. We call theta the inertia, and omega dot is the angular acceleration. All right? So by definition, we have this equation as well, because when a body is rotating about axis of symmetry, it gets torque, right? And the definition is this one. So this term is equal to this, because both equations, they are representing the torque of the ball around the center of mass. So ds is going to be equal to tau. Then we can write mu m gr equal to theta w dot. All right. We are doing this because we want to clear this expression, this term. We want to clear the acceleration. So if we have this, we get the angular acceleration omega dot is equal to mu m g r theta. So this is I will talk to this real fast. This is the same as derivative with respect to time of the angular velocity, or some people or some books call this expression as alpha. So it's just notation. Whatever notation we can use is fine. There is no big deal with it. We are just using the dot notation, and that's it. Okay, guys. This is the angular acceleration for now. But for a ball that is rotating about its center of mass, for a ball that is rotating around the center of mass, the inertia is defined by 2/5 of the mass multiplying the radius square. Okay, guys. And okay, I forgot real fast. I wanted to call this equation number 2. I forgot it. That's it. Okay, we come back to the inertia of the sphere, of the solid ball, and by definition is this. Okay, we replace this equation into the previous equation that we calculated for the angular acceleration, and our equation is going to take this this way, omega dot is equal to mu mass gr dividing 2/5 of the mass radius square. So we simplify some expressions here that are similar, like the masses. These are with this one. The expression finally is going to take this way, phi dividing 2 mu g dividing r. Then finally our angular acceleration is going to be phi mu g dividing 2r, and we will call this equation number 3. All right. Okay. We have this equation here, and we will use it in a little bit, but we want to take into account that we have a friction force. That friction force, the consequence of this friction force, or the result that it has just on the ball, is that it decelerates the ball. So it starts like making the ball moving slow and slow. So that is a deceleration. We know the second Newton law, right? The second Newton law, we have it like force is equal mass multiplying the acceleration. If we have a body that is moving with some acceleration, and obviously the body has a mass m, the force that is making the body to move with that acceleration is defined by F, by the second Newton law. Right? So but the acceleration in this case is going to be negative, because the body is decelerating. So because of this situation, we are going to have minus F is equal to mass multiplying the acceleration, because F is equal to minus F on this situation. So this equation is going to take this form, and we have it like that. Then the acceleration of the ball is going to be something like minus F dividing the mass. Obviously, A is the acceleration of the center of of mass. And we know the center of mass is just in the at the center of the ball. Okay. So let's call this equation 3.1, and we will use this equation later in a little bit. For now, we have this equation here, and let's hold on with it and keep moving. We will use it in a little. Well, let's talk about something. The rotation, for the rotation velocity of the ball, because I mean the velocity for the rotation when the ball is rotating, it can be calculated using equation number 3, because we know that on equation number 3 we have the angular acceleration. We have the angular acceleration, right? So because the angular acceleration is the derivative of the angular velocity with respect to time, then to calculate the angular velocity we need to perform the integration of the angular acceleration with respect to time. All right, so we go from t equals 0 to t equal t, because the ball starts moving on t equals 0, but we know that on that time on t0 the motion is purely translational motion. It is not, it's still rotating. So on t equals 0 the ball is sliding, and we want to calculate when t is equal to some, when t it has a ball, when the time has passed and we have t, the time t, the ball is going to start moving, taking a rotational motion. So it has to be calculated, right, using this equation right here. Well, let's do this real fast. We have, by definition, as we talk about it, that the velocity, angular velocity, is equal to the integral from t equals 0 to t equal t of the angular velocity with respect to time. Okay, but we remember that we calculated the angular acceleration on equation 3, and we replaced that equation number 3 into this equation. We remember that angular acceleration is phi dividing 2 coefficient friction multiplying the gravity dividing the radius. All right, so this is the angular acceleration that we calculated on equation number 3 right here. Okay, we come back and we write integral sine from 0 to t with respect to time. This term, as we know, it has to be outside of this integral sign because it's a constant. Phi dividing 2 is a number, mu is a constant, gravity and the radius, they are constant, so it's right down outside of the integral. We know that. So, and the integral from 0 to t of the t is t. And this equation is going to take phi dividing 2 mu g dividing r multiplying t. And we call this equation phi 2 mu t mu g r t. We call this equation number 4. Okay, we have equation number 4. Let's see. We have the angular velocity, angular acceleration, sorry. We have the angular velocity. But now we are going to talk about the linear velocity. Remember, the body is it has a linear velocity because it has a deceleration that we talked about on this equation, equation 3.1. Right? And eventually, obviously the ball has a linear velocity. So let's talk about it. Let's talk like Let's see now the linear velocity of the center of mass is calculated from equation 3.1. Where is equation 3.1? Is right here, right? It's right here. Let's write it down. We remember that the acceleration is equal to the derivative of the velocity with respect to time. Then the velocity is equal to the integral of the acceleration with respect to time. All right. So, but we have our acceleration here, and we are going to write down the acceleration on this formula into this formula. Then we have integral from 0 to t of the acceleration, where the acceleration for us was minus f dividing m dt. Oh, let's see something we don't have here because we are starting the acceleration from t equals 0. So then the acceleration is equal to, okay, the equation is going to be a equal to, oh sorry, it's v equal to integral, okay, minus f dividing m integral dt. But we know that the friction force is defined by the coefficient force or friction coefficient multiplying the weight of the ball. In this case is mass multiplying gravity dividing the mass integral of dt. We simplify the similar expressions or terms, and we get this like mu g integral dt. And this is equal because this is we don't have limits on this integral because we know that we want to calculate the initial velocity of this ball or the ball. Yeah, we want to call the initial velocity. Let's do something. It's gonna be mg plus c, where c is the integration constant. We don't have limits here because we have the ball starting with a velocity, and we want to calculate that velocity. I mean, on t equals 0, the ball has a velocity, it gets a velocity v0. We want to calculate that velocity, right? Okay. Let's call this constant c, let's call it v0 for convenience. We call this constant c equals 0 because remember that the constant gives you the initial conditions of the problems. So we get v equal to mu g t plus c. Oh, remember something. I forgot to write this sign here, minus, because this is minus. minus here 2, then this is minus, right? This constant c is v0, then v0 is equal to, we send this term to add on the other side of the equation, v plus mu gt. Okay. But if we remember, we calculated, if we remember, this is the, we calculated the angular velocity of the ball, right? And let's see, we know that v is equal to angular velocity multiplying the radius. All right, so we have v0 equal to omega r multiplying mu gt, but omega by definition is, we know that v, okay, we calculated this here. Now we remember that we had omega on the last equation, number 4. So we replace equation number 4 into this equation. And when we do that, we get phi dividing 2 mu grt, mu grt plus mu gt. Okay, and we have okay, this is omega. Okay, I forgot to write something. This is omega, and we have r plus mu gt. We simplify similar terms, and we get the same, the following equation: phi dividing 2 mu g mu g. Okay, I have a t here, mu gt plus mu gt, and that is equal to 7 dividing 2 mu gt. Okay, this condition, why I did this? Because the condition happens when the billiard ball starts rolling, starts rolling, when this happens. So that's when I use this equation and I replace it on the equation of the velocity, right? So that's the condition. The ball starts rolling when the velocity is equal to omega multiplying the radius. All right, so let's keep going, and we have v0 equals 7 dividing 2 mu gt, then t is equal to 2 dividing 7 v0 dividing mu g. And let's call this equation number 5. Okay, I had equation number 5 before and I forgot to write it to is this one. I forgot to write this equation line number 5, and this is equation number 6. Okay, we have the time when the ball gets the velocity. Okay, the velocity v. initially the velocity is v0, but when the time is t, the velocity is defined by number 6 equation. And that happens when the ball starts rolling and gets rotational motion. Okay, guys? That happens, this time is just when the ball starts rolling. We need to know that. Okay, let's see something. Okay, the distance, we want to calculate what distance the ball traveled before starting rolling, because it started initially having a translational motion, but when that translational motion changed to a rotational motion, the ball, before that happens, it moves a distance. So the ball, let's see that the ball started moving right here at this position, and it glides this distance s. But when the ball started having just a motion of rotation, it traveled a distance s. So we want to call, or we want to find that distance s. All right. How do we do that? How we do that? We do it like, because we know the velocity is the derivative with respect to the time of the distance, then the distance is the integral. Then the distance is the integral with respect to the time of the velocity. Okay. We know that the distance on t equals 0, the ball goes from t equals 0 to t, to move from the linear motion to rotational motion. All right. So because of that situation, we calculate the integral from 0 to t. And we know that the velocity is, we remember that the velocity is v0 minus mu g t, right? We have it here, right? On this equation number 5, we are replacing equation number 5 into this formula. This is dt. So the distance is s equal to v0 integral. What I do is I distribute the integral into these expressions into the parentheses from 0 to t of dt minus mu g integral from 0 to t dt. All right. And we have this equation. Then s is going to be equal to just the integral of dt is t. So we have v0 t minus integral of dt dt is t squared dividing 2. Okay. But that time is the time that we calculated on equation number 6. So we have to replace equation number 6 into equation number 7 that we call here this equation number 7. So 6, we replace 6 into 7, and we get the following equation: s equal to v0 multiplying 2 dividing 7 v0 dividing mu g minus mu g dividing 2 dividing 7 v0 dividing mu g square. Okay, remember that we replace 6 into 7. We have 7 right here, and we have equation number 6 right here, and I replace 6 into 7 and I got this. Okay guys, let's keep going. Then the distance s is gonna be something like okay, let's do something real fast. Okay, v0 is gonna be v0 squared. All these terms are gonna be a square, right? So I'm gonna get something like this: 2 dividing 7 v0 squared dividing mu g minus mu g dividing 2 multiplying 4 v0 squared dividing 49 mu squared g squared. So I cancel similar terms, right? And I get s equal to 2 dividing 7 v0 squared dividing mu g minus, okay, this 4 simplifies with this 2, so I get 2 v0 squared dividing 49 mu g. Okay, this I multiply these terms by 7, I mean by 2 by 7 and 7 times 7. That way I get 14 dividing 49, and I get similar denominators, and I can do this of the terms. So they would be 14 minus 2 is 12 v0 squared dividing 49 mu g. Then finally the distance s traveled by the ball is 12 v0 squared dividing 49 mu g. This is the distance that the ball travels before it starts moving with a rotational motion. Okay guys, hopefully this problem helps you to understand some physics, and see you next time. Bye.